Lesson 74. In this lesson, we will formally introduce the technique of integration by substitution. By now, you should also notice the standard integrals found in your formula booklet. By doing your homework, you should become very familiar with these, and you'll be able to find the integral of standard functions automatically. But it is not a bad idea to familiarize yourself with what's actually available to you in the formula booklet, just in case. In the last lesson, we talked about how we can integrate functions by inspection if an integral takes the form of f of g of x multiplied by g prime of x. I have actually shown how sometimes we'll let u to represent a function g of x so that we can replace part of that original function in terms of du and write it as a function of u. In that way, it helps us to simplify the work that we have to do, and we can recognize the patterns in the function that looks like one of the standard integrals. You can take a look at the notations here. We use uppercase F to represent the antiderivative of the function f of x. So we say that the derivative of the antiderivative at g of x must equal to its own derivative multiplied by g of x, and this is because of chain rule of differentiation. And of course, the derivative of the antiderivative will become the function itself. So now, if you take the integral of that expression that we've just gotten, you will end up with f of g of x plus c, f being the anti-d. Okay, it's just reversing the differentiation. And so if you replace g of x in those expressions with f of u, then you'll see what happens in the formula. It looks very complicated in this derivation. In practice, it really depends on how much homework you do for you to become very comfortable with integration. So let's begin looking at some examples here. If you're confident, you can pause the video at any point, try the questions before you turn to the solutions. 1a. Integrate 4x minus 1 cubed dx. Here I know that the basic function is a cubic function. I'm going to let u to be 4x minus 1. Du then turns into 4 dx. Or I can then say du over 4 is actually equal to dx. It is very important for you to notice that you cannot see this as a cross multiplication. So let me write a note here for you. This is not cross multiplication, but the theory is beyond the course, okay? Now we can write the function in terms of u and take the integral with respect to u. I have the integral of u cubed du over 4. I'm going to write this over here instead. I know that when I integrate u cubed, I get u to the power of 4 over 4, but I have the original 4. So let's stick it in here, plus c, meaning my final answer is 4x minus 1 to the power of 4 over 16 plus c. Question B. Here I have the integral of 5 over 3x plus 2 dx. Now the 5, I can easily pull it out. And I'm looking at 1 over 3x plus 2. This format reminds me of 1 over u, which is related to ln. I'm going to let u to be 3x plus 2. Differentiating this, I get du equals to 3 dx. Or dx is 1/3 du. So here I can have 5 over 3 integral of 1 over u du, which gives me 5 over 3 ln absolute value of u plus c. Back substituting, I have the following. Number 2, 2a. Let's take a look at the integral of e to the power of x over e to the power of x plus 1 dx. What will be a useful substitution? To me, if I let u to be e to the power of x plus 1, then du is e to the power of x dx. Perfect, because I see it right here. Now I can write this integral as 1 over u du. I know this is ln of u plus c. Skipping that step, ln of e to the x plus 1 is my final answer. Question B. I have the integral of 3x squared cosine of x cubed plus 2 dx. Well, usually the angle inside a trig function is what we're more interested in, or we'll start there when we think about the substitution. Think ahead before you write this down, right? If you look at x cubed plus 2, what is its derivative? Seems to be useful, right? Because it is 3x squared. So du is 3x squared dx. Why do I like that? Because here we have 3x squared dx, which can be replaced by du. And I have integral of cosine u du, which gives me sine of u plus c, or this is sine x cubed plus 2, and then plus c. Question C. You have the integral of 2x cubed times the square root of 4 minus x to the power of 4 dx. When you differentiate a function, a polynomial or power function, you should notice that, the degree of the function goes down by 1, right? So when you're picking what to substitute, you're more likely to find success if you let u to be the function that has a higher degree. So here du is negative 4x cubed dx. This is not entirely the same as 2x cubed dx that I see in my question. So if I want to make it more clear, what is 2x cubed dx equal to in this case? That would be du divided by negative 2. Now I can say that I have negative 1/2 integral of u to the power of 1 over 2, because that's the square root, du. Working further, I have u to the power of 3/2 times 2/3 plus c. Simplifying the coefficients and also substituting back 4 minus x to the power of 4 as u, I get my final answer. Question D. I have integral of 1 over x ln x dx. I see ln x. I see 1 over x. What's a better choice as a substitution? Knowing that ln x has a derivative of 1 over x, you see how we actually have 1 over x in the question? That means this can be turned into 1 over ln x, or 1 over u, du, which is ln of u, which is ln of x, plus c. So we have ln, absolute value of ln, plus c. So it certainly takes some creativity and also intuition when you are doing these integration by substitution questions. But don't worry, it really does come with practice, okay? Example 3, evaluate. So in this example, we're going to look at definite integrals. Example A here shows a product of the cubic of a cubic function multiplied by a quadratic function. From what you have learned on the previous pages, you probably can see that, well, if we let u to be x cubed minus 3x plus 2, then du will be 3x squared minus 3 dx. It doesn't match up with x squared minus 1. However, if I divide both sides by 3, then this is what I'll have. So we can get that substitution in there nicely. The next question, though, is that now we are talking about definite integrals. We have boundaries. We want to evaluate this when x is 0 from this to x equals to 2. But once I complete my substitution, so let's take a look. I have u cubed du over 3, so 1/3 here, right? Once I sub in the u's, it's silly to write my boundaries using x. So what we should be doing then is to work out the u values as our boundaries, okay? Let's start with the lower bound. The lower bound when x is equal to 0. I have 0 cubed minus 3 times 0 plus 2. That means my lower bound is 2. My upper bound, let's call this u2, is 2 cubed 8 minus 3 times 2, 6 plus 2. So 8 minus 6, 2 plus 2 is 4. So here is the proper way of writing this substitution with the correct boundary. So here we can integrate u cubed, goes into, it becomes u to the 4 over 4, from 2 to 4. So 1 over 3, 4 to the power of 4, over 4, minus 2 to the power of 4, over 4. This is not bad. His first term is 64. Second term is 16 over 4, which is 4. 60 divided by 3, that's 20. Okay? Now, what if you're questioning, well, does it really make a difference if I have to start here and then back substitute x cubed minus 3x plus 2 back into this expression and then use my original boundary to evaluate my answer? Well, let's compare, right? So here what I can do is I can pull out that 4 as well to make it easier. So substituting 2, I have 8 minus 6, 2, 4, 4 to the power 4 here, minus 0, 0, 2 to the power 4. So 4 to the power 4 is 256. And then 2 to the power 4 is 16. This is 240. 240 divided by 12 is also 20. So as a result, you do get the same answer. But in terms of format, you know, when your function is written in terms of your boundary should show these values, 2 and 4, reflecting the values of u. Okay? Let's take a look at question B. So here I have the integral of sine square x cos dx from 0 to pi over 2. So I'm going to let u to be sine x. So now du is cos x dx. Perfect. You can also make your adjustments for the boundaries here. u2 is sine pi over 2, which is 1. u1 is sine 0, which is 0. So putting this all together, we're going from 0 to 1. U is sine, so u squared. Cos x dx is now du. This gives me u cubed over 3 from 0 to 1, which is 1 over 3 minus 0. Simple. Question C. The integral of cubic secant x tan x dx from 0 to pi over 3. Okay. Now let's plan, because this looks complicated. Let's start with the easier substitution, potential substitution. So if I let u to be tan x, du, what is it? It is secant squared x dx. What does this allow me to do? It allows me to take away 2 of the 3 secant, and then I'm going to have something like this. I don't think that's the most useful thing that I can think of. Well, let's try another option. What if I let u to be secant x? If you don't remember what it is, you can use your formula booklet. The derivative of secant is secant x tan x dx. What does that mean? That means I will have one of the secant from that cube taken away, right? But essentially, I will still have secant squared x, and then secant tan dx all become du. Is this something that we can do? Well, at least I know how to integrate the square of secant x. But it's in terms of du, so I shouldn't have an x in there. What can we replace that with? Well, don't forget, secant is u. That means this is a more useful substitution for us than letting u equals to tan x. Okay, so let's write this out properly. If I let u to be secant x, I will end up with the expression u squared du. I'm very confident that this is an easy integration now. Another thing that I should not forget to do is to evaluate my boundaries. So u2, the top number, when x is equal to pi over 3, I need secant pi over 3 instead. u1, I need secant of 0 instead. Okay, so cosine of 0 is 1. Flip it, 1 over 1 is 1. Cosine of pi over 3 is 1 over 2. Reciprocal is 2. So 2 and 1. Keep going. U cubed over 3. From 1 to 2, I have 8 over 3 minus 1 over 3, which is 7 over 3.